So the course is called Introduction to Combinatorics. And here is a definition of a combinatorial object by Adriano Garcia. So Garcia is, he's still active. There was a 90th birthday celebration last year, and he was still very active even at that time. And then he wrote this very nice thing. He says, "What is a combinatorial object?" And his answer is a visual representation of a mathematical construct. So this is our goal, to try and see the visual representation of many combinatorial, many mathematical constructs. So today we are looking at the binomial theorem, which you are know since high school, but we'll do an additional. Hopefully, we'll get time to do an additional, theorem in the, for the Q binomial theorem. And Shivam's role is more to help in technical matters in this course. So normally for calculus and other courses, TFs are responsible for helping you with the math. Here he's essentially helping with the technical matters. And if there's any issue or any question on the mathematics or grading, etc., that has to come to me. There is a course website. There's a Google Classroom, which is good for announcements. We'll use Gradescope for assignments, midterm, final. So everything is going to be take home. There are lectures on Zoom, and we are going to use Sage Math. So Sage Math, I want everybody to download and install if possible and get it working. Assignment breakup, there are going to be 5 assignments once every 2 weeks approximately for 20 points, 1 midterm and 1 final. So I suggest that you discuss with each other, but write answers on your own. So you can discuss, so I would say, I normally think at this level, I would think for 2-3 hours on my own, and then I'll find the answer somehow. And then, but when I write the answer, I internalize it. So I will share techniques of thinking with you as time progresses. But keep this in mind that, you try to do it on your own, but you by and large, you get to know how to do them. And the focus should be on, your focus should be on problems. I've listed the dates. It's pretty much every 2 weeks there is a submission. And I'll give an assignment maybe after a week, and it covers, couple of weeks work. Again, whatever you learn, I don't think you learn so much in lectures, except that you get, some techniques for how I think. That's all. What you really get is when you do the problems. So lectures are just about figuring out how to think. Problems is the real thing. So, my prof earlier used to say that you should look out of the window when there are proofs going on in the class. But when that's homework, then that you have to do on your own. So you can always read my notes later and read proofs from elsewhere and so on, but it's important to find your own proofs. So the classroom or the lectures are more on, trying to figure out, this is a way to think, I mean, this is not the only way to think. This is a way to think. And even amongst combinatorics guys, this is not the best way perhaps, because I'm not the best combinatorics guy. But anyway, so lectures are more for entertainment, and problems is where the real work happens. Collaborative, most of mathematics done today is collaborative. You should first try on your own, then discuss with others, but write your own solutions. And in writing solutions, think about communicating the ideas and the approach. So you're not just solving the problem. And if you get an idea from a friend or somebody else, then you should give them credit. Okay. So make pictures, provide. So you are trying to say that, okay, I'm able to do this problem. And everybody in the class should be able to do every problem. There should not be at the end, any problem which is left undone. So don't think of this homework as that there are 5 questions, I'll do 4 and that's it. Think of doing all 5. Everything has to be done, should be done. And if it's not done in the first, you finish it at some later point. Here's a definition which I shared with my calculus class. What does it mean to understand something? when you can explain to a younger brother or sister in terms of things they can understand. So you should be able to go one level below. Zoom, keep mic muted unless you need to ask me something. Please do interrupt, especially when I'm making mistakes. I'm unable to view the chats, and this applies to me as well. I've tried my best to fix my environment, but I get thrown out of Zoom. So I expect somebody to call me, Shivam, to log back in. Just stay there. I'll get back. Okay. Any questions? So the course is introduction to combinatorics. So first of all, what is combinatorics? And the joke is that it's combinatorics that counts. Well, it's somebody's quote. I don't know whose quote it is. So what is counting? So we are starting from the very beginning in some sense. So this is trivial stuff essentially. But let A be a finite set. Uh, the cardinality of A. By the way, I don't think I will be sharing these notes which I'm writing over here with you. So take your own notes. I think there is some level of understanding which happens if you just copy whatever is on the board. So even though this is available as a e-file, I don't think I may be sharing it. I mean, I might share it, but I doubt it. So cardinality of A denoted by this is the number of elements in A. So sometimes we will just write like this. So for a sum of ones when A belongs to A, and this is for finite sums. Okay, and so this is one point. The second is when are two sets. So this is fundamental. Two sets uh, have the same cardinality. When um, they can be put in one-to-one correspondence with each other. So this means I there is a bijection between. So I hope you know what a bijection is, right?
Yeah, Professor.
Okay. I hope I know that too. So anyway, the first proposition is fundamental counting principles So a lot of what I'm writing in the first couple of propositions is often left unsaid in combinatorics and in math in general, uh, because but it's sort of useful to know when you are sort of writing a proof, whether it is are you hand waving, or is it a sort of rigorous proof. So sometimes this is used and we will use it. I'll show you how it is. So let S1 and S2 be finite sets. Okay, so the first part is that let S1 intersection S2 be empty. Then the cardinality of S1 union S2 is the sum of the cardinalities of S1 and S2. And the second is um, let S1 cross S2 be the set of ordered pairs, where A belongs to S1 and B belongs to S2. Then the cardinality of S1 times S2 is equal to, or cross product is equal to S1 times S2. So it's fairly obvious, but we'll give a proof. So the cardinality of S1 union S2 is the sum over all S belonging to S1 union S2 of 1. And then um, why can we say this? We can say this because S belongs, so because either S belongs to S1 or S belongs to S2, but not both. So an exclusive OR. Why not both? Because S1 intersection S2 is S1 intersection S2 is empty. And then this is equal to S1 plus S2. And for the second one, uh, here is the technique. For fixed S belonging to S1, let U of S be defined as, so I'm using this term, right here. This means defined as. I understand there are some computer science students here. They may know this notation. So U of S, for fixed S, you consider this set S of T, where T belongs to S2. Okay. So how many elements are there in U of S?
Cardinality of S2.
So S is fixed and there are, you put T. So the same, so the number of elements in U of S will be S1, the cardinality of S1, not S2, sorry. Right? So there's a one-to-one correspondence. Why? Because there is a one-to-one correspondence and so on. So there's a one-to-one correspondence with elements T of S2. Okay. So now what we want to see is that S1 times S2 is a union of U of S. So there are two U's. That's a bummer. So union of this, and it's a disjoint union. So by part one, and induction, we have S1 times S2. Cardinality is the sum of the cardinality of S, where S belongs to S1. And this we just saw is S2. So cardinality of S belongs to S1, S2. S2 is common here, so you can take that out. This is 1, and that is S1 times S2. So that finishes the proof. Okay, so the remark is, this is a very, very important idea. This is called counting in two different ways. In fact, remarks. So let A, B be a pair of sets, finite sets. Suppose for a given A belonging to A, U of A is equal to, again similarly, A comma B, B belongs to B, and for a fixed B in B, U comma B is A comma B, A belonging to. So here B is fixed, and this let's call it V. Okay, then we must have the sum over A belonging to A of UA should be equal to the sum of B belonging to B of B. This is called counting in two different ways. So we count. So in combinatorial proofs, many times we count pairs of such objects, and one we fix one, we say A, and we count. We find out what is the cardinality of U of A, and we count B, and in both of them, basically it's U cross B, and then we compare the two. So that is what is meant by counting in two different ways. You can extend the proposition to n sets, S1, S2, Sn. So A, suppose S1, Sn are pairwise disjoint. Then product or union of Si should be equal to summation of Si. And B, S1 cross S2 Sn should be equal to S1 times S2, so on.
Professor?
Yeah.
Will it be cardinality of UA above?
Yeah. You're right. Thank you. Absolutely. Yeah. Okay, so these are, this is, I think, chapter 0, whatever we just did. This will be used repeatedly, sometimes hidden, but it will help you, make sure that your proofs are sort of, when sometimes the combinatorial proofs are a little bit like a hand waving type of thing. So this usually helped me in clarifying sometimes what the proof was, and sometimes we just use it as it is. This was I. All right, so let's go on to the main topic. Let me call it chapter 2, and this is the binomial theorem. Okay, so it's quite long. Well, not so bad. All right, any questions so far?
No, Professor.
Okay, I mean, just feel free to interrupt me, okay? I mean, not just to point out, I mean, of course, to point out my mistakes, but otherwise to, if there's something, I mean, if you can't read my handwriting and so on. So I can't read my own handwriting, so I don't mind to tell me I can't read your handwriting. I'll try better. Okay, so this symbol is defined as uh, is the number of. So I use this for number many times. So this symbol is n choose k. It's read n choose k, and it's the number of k subsets of an n set. And a prototypical of an n set, we use the symbol in, which is 1, 2 till n. Right? And the theorem is, which you have learned earlier, that if I expand x plus y raised power n as a polynomial in x, uh, then I get this polynomial in x and y. Okay, and this is true for n equal to 0, 1, 2, and so on. So the idea is as follows. So I'm going to give a different proof than what was there in your NCRT book. Okay, don't mind, I'm drinking my coffee. It's 5 o'clock. They say mathematicians convert coffee into theorems. A mathematician is a machine for converting coffee to theorems. So I don't have too many theorems yet, but I'm trying. So anyway, the idea is, let's just do one, x plus y, x plus y, x plus y. And it has various terms when you expand it out. So suppose, so one of the terms is x, x, x. Okay. And this uh, I link with a binary string. So I link with 0, 0, 0. Then suppose I take an x here and then an x here and a y here. So I have this. This I link with a binary string this. I could have this. I link with a binary string. So x's I replace by x, y's I replace by 0. Now, all these binary strings have exactly 1 in them, and they contribute this term, x square y. And similarly, we can have two y's, so x, y, 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 x, y, and y, y, x. And these are linked with 0, 1, 1, 1, 0, 1, and 1, 1, 0. And these contribute the term x, y square. And finally, I have this term. So this contributes the term y cube. Okay, so the idea of the proof is you link these products with the with binary strings. So let x plus y raised power n be equal to summation bk x raised power n minus k y raised power k, going from 0 to n. Then bk is the number of binary strings of length n with exactly k ones. Fine. Now, this, the binary strings, or rather a binary string with exactly k ones. So let's say suppose it's a1, a2, an. This corresponds to a subset, k subset of in, which I'm defining as here. So these are AIs are either 0 or 1. So I take the i's where AI is equal to 1. So for example, here's an example. I have this binary string 0, 1, 1, 0, 0, 1, and 1, 2, 3, 4, 5, 6. So n is equal to 6 and k is 3. So I don't take the first element, but I take the second element, I take the third element, don't take 4 and 5, and I take 6. So you can see that there is a k subset of in, and that proves it. That does it. That proves our theorem. And you immediately have, so I don't have a formula yet right now, but I immediately have this theorem. And remember, the theorem simply said that x plus y raised per n, this guy is going to be n choose k. Something wrong here. Should be x raised per n minus k. So let me. So I made some correction here. Anyway, so one immediately has n choose k is equal to n choose n minus k. Why? Because replace, or rather interchange, zeros and ones in the binary strings. So there are some binary strings which correspond to, these guys. If you interchange the zeros and ones, you'll get n choose n minus k. And then those two numbers have to be the same, right? And another remark is that it is enough. So I used x and y's, but it is enough to write 1 plus x raised per n equal to. So you don't need the y's. So n choose k, x to the k. I mean, the y is an additional parameter, and the reason is that you can replace x by y over x to get the outcome. So you'll see this form most of the time, but I needed the x and y's for some reason. And you will get to know the reason shortly. Is that okay? Is the proof okay?
Professor, could you just repeat the last line of the proof? Thanks.
Last line of the proof.
Yeah.
So the idea is you have x plus y. You have x plus y raised per n is equal to this bk. So bk is the coefficient, and bk is the number of binary strings of length n with exactly k ones. Now, any binary string with exactly k ones corresponds to a k subset of in. So whenever you have a 0, you don't take that element. When you have a 1, you take that element. In is, remember, in is 1, 2, 3 up till n. So, you take the i's where ai is equal to 1. Don't take the i's which are 0. And so, for example, if you have 0 first place, so don't take 1. 1 in the second place, you take 2, 3, 4, 5, you don't take 6, you take. So any binary string with exactly k ones corresponds to a k subset of in. So bn is the number of binary strings of length n with exactly k ones. That has to be the number of subsets, k subsets of n sets.
Okay, Professor, makes sense.
So yeah, I mean, it's like trivial after that. That's that's
Thank,
combinatorics
yes,
for
thank
you.
you.
Most people say, oh, it's trivial, but it's also very interesting and fun. It's not so trivial. I mean, when you see it, it's trivial. I mean, that's so. Polya, I have to tell you this. This is my favorite quote. Okay, before I write my favorite quote in math is as follows: Beauty in mathematics is seeing the truth without effort. This is by Polya. Do you agree? Do you guys agree?
I would love to agree, but effort is still needed for me at least.
Uh-huh.
At the moment, effort is still needed.
No, of course, effort is needed, but once you see it without effort, that is when you get a sense of beauty, isn't it?
Yes,
I mean,
Professor.
the effort is effortless. Is the effortless appreciation is after a lot of effort, but once you see it, then you really understand that it's beautiful. So, I mean, when you're writing or when you're presenting or when you're thinking, then you try to say, okay, do I understand it enough to make it effortless? And that's it. Anyway,
So,
so back
Professor,
to
I
yeah.
think once we start effortlessly seeing like the beauty of math, like that's when we'll realize the beauty of this quote as well.
Yes, yes, but yeah, so I just want to say that it's not that you will ever, I mean, you may be Terence Tao or Manjul Bhargav, then you will see perhaps without any effort anything, maybe if you are that guy, but uh, one has to work very hard to get to a stage where you see the truth without effort. So I'll just show you another proof and you'll see that, I mean, once you see it, it's trivial. I mean, this is trivial once you see it, but it's not, why isn't this in NCRT, for example? This is easy enough to put there. Why didn't they put it there? Why did they prove it by induction and this and that? So it takes some effort to get to that, but once you get then, so that is what Polya meant, that it's when it is effortless, then only it's beautiful. And of course, to achieve that effortlessness, you need a lot of effort on your own part. So don't think that you will ever come. There will ever be a day when everything will appear beautiful. For sure, that will never happen. I mean, unless you are Manjul Bhargav, which if you were there, then you won't be sitting in this class. So anyway, so here are some properties. I said. So I mean, I wanted to go a little bit fast, but my handwriting gets worse and worse as I go faster. But I think it's improving. Definitely from calculus, it's much better right now. So these properties which I'm listing right now are allow us to calculate n choose k. So far I've just said that 1 plus x raised power n is this number. I don't know what that number is. So so I need to find that number. So here is the properties. So first of all, 0 choose 0 is equal to 1. Secondly, 0 choose k is 0 for k bigger than 0. N choose 0 will be 1 for any n. I mean, that's, n equal to 0, 1, 2. N choose n is equal to 1. And then finally, n plus 1 choose k is equal to n choose k plus n choose k minus 1. So 1 to 4, these are sort of obvious from this guy, or x plus y. I mean, what are you saying? If when k is 0, then when k is 0, the first term is going to be x raised to n. That's what the first guy is saying. When k is n, the last term is going to be n. So it's sort of obvious because when you are writing x plus y and multiplying it together, these two things, and then this is 0, and this is just simply saying the first term is 0 and the last term is 1. Sorry, this one is saying there is no term which is beyond when n is bigger. In fact, it could be n choose k 0 when k is bigger than n. So I could write n choose k 0 for k bigger than n. If n choose k is defined like that. Anyway, so this one I'll prove, and I can prove it from here pretty quickly, but I want another proof. So proof of 5, I'll try to give a combinatorial proof. So the left hand side, n plus 1 choose k, is the number of um, binary strings of length n with, n plus 1 with exactly k ones, right? This is what we said. So put them in two buckets. So bucket 1, I mean, it's like, you put milk in two buckets. Bucket 1 is where n plus 1th, um, the n plus 1th entry is 1. And bucket 2 is when it's 0. So it's a binary string of length n plus 1. Put them meaning all the binary strings. So you take n plus 1, choose k. These are the number of binary strings. You put them in two buckets. The last entry is 1 and the last entry is 0. How many of these are there? So last one is 1. Right? So the number is basically, the rest of them are k minus 1. N choose k minus 1 because the last one is already 1. So the first n entries will have k minus 1 ones, right? And how many of these are there? Last one is 0, so all the ones come in the previous n ones. So what does this tell you? Therefore, well, I don't like this. Sorry. Do you see that? Do you see the proof? So this comes from bucket 1, and this comes from bucket 2, and we are done.
Professor, in bucket 1, I didn't completely understand it. How it is nk minus 1?
You have, let's say you have, so you have n equal to 5, let's say, and you have this 0, 1, and the last one is 1. So this is bucket 1. So if we delete the 1, what is left is a n equal to 4. So this is n plus 1 equal to 5. And you have number of k's is 1 less. It's 2.
Yeah. Okay, thanks. Yeah.
And bucket 2 is where the last one is 0. So you have, for example, you have k equal to 2. Suppose this is the case. So if you delete this guy, this is just, n equal to 4 and k equal to 2. K equal to 3, sorry. No, there's something. Yeah, there should be one more one. So here I'm taking k equal to 3 and n plus 1 equal to 5. So I mean, you just delete one and then it's either here or there, and then obviously those three things will add up. Those two things will add up to give what we get. That's right. Okay, so the point of this proposition right here is that you can calculate and choose k. So this is an example of what is called a recurrence relation. So favorite interview question a friend of mine used to tell me. He was interviewing people in the software industry. So he said his favorite interview question used to be, give a recurrence relation example of a recurrence relation which is different from n factorial. Everybody just remembers that. So anyways, this is one example. So the benefit of this proposition
Professor,
is, yeah.
do we conventionally take that when n is less than k, that the boy n choose k is 0?
Not necessarily. I mean, depends on the context. So that's why I didn't write it over here. But I mean, I wrote it here, but I didn't write it in the proposition. So yeah, there are different conventions for that. But yeah, typically it is taken to be when n and k are integers. When n and k are positive integers, then it is 0.
Okay,
But
Professor,
some,
thank you.
I mean, one could have definitions where n is a real number, and then there are some other
Right.
concerns. So yeah, for now, I mean, yeah, it's 0. So we can calculation is wrong, but we can calculate and choose k, and just make a table. So this we know. So let's say this is n and this is k. So this is 1, 1, no, yeah. Then this is 1, this is 2. Now how do I get the 2? So this I'm getting from 2 choose 0 is equal to 1. And this one I can get as a sum of these two guys. And then this I get as 1. So I'll just explain 1, 3, 3, 1. So I'm taking the sum of, let me do 1. So let's say this guy, if I add these two up, I get this. So this is n plus 1 choose k. Then I go to the previous line and I take n choose k, which is this chap. And then previous line, go one before. Right? So 1, then 5 is 1 plus 4, then 10 is 6 plus 4, then 5, then 5, then 1. Have I made a mistake? Sorry. 10 is 6 plus
10
4.
again, Professor, right?
10 again, 10 again. Sorry.
It's sort of a Pascal triangle, right, Professor?
Yeah, it is called Pascal's triangle. Thank you. So
So
yeah, I mean,
what is
Pascal's
the
triangle.
last? What is the last?
Huh?
What is the last entry 1 in the fifth column? Sorry.
Yeah, so this comes from n choose n.
Oh, okay. Okay, it goes
So
3, 4, 5. Yeah.
yeah, so now if we go back, you'll see why I wrote all these guys. 0, 0 is 1, 0k is 0. So beyond this point, all are 0. In fact, n choose k is 0 for k bigger than n. That means all these entries are considered 0. This is 3, 4, 5. And n choose 0, first term is 1, last term is 1, and these are made of the previous two guys. Okay, so that's Pascal's triangle, and let me say that this was known, you know, so this is like, it sounds like a claim by our government, but it is actually true. It was known in ancient times in India. I don't know exactly what. So there is some, in the context of music, it came up in India. And it was known in China at least 1303. There's a guy called Chu. I mean, most people in China are called Chu, so that's not saying much. But there was a chap called Chu who wrote this, who wrote this Pascal's triangle. Pascal himself was long, much later. I don't know, maybe seven. I'm not sure about the history. So when I write the notes, I'll check the dates. This was possibly 10th century or something. I mean, this was really long back. So, I mean, people have had time to relook at it in many different ways. Okay, so what I want to do, I mean, so all this is fine. I mean, this is high school stuff. And, you know, Bhatia was concerned that I will only do high school stuff in the course. So I, you know, sort of promised him that I'll have at least one more thing beyond high school. And here it is, at least one more thing. So we want to generalize it to the non-commutative case. So what do I mean by that? What I mean is XY, so suppose X and Y are such that Yx is equal to Qxy and Q commutes with X and Y. That is Qx equal to Xq and Qy is equal to X. So this is known as, well, it's known as, so we want a binomial theorem like that. And this is, again, I don't remember exactly when, but Furstenberg gave this theorem. Not sure when, and I'm not sure who it is. I think it's a physicist. So it came up, this came up in the, so these are called Q commuting variables. So something to do with quantum, perhaps. I don't know, I'm not sure.
Professor,
Yeah.
X and Y don't commute with each other, right?
Yes.
And here in the second line, you've written Qy is equal to Xy. So you're on the bottom, you've written and Q commutes with X and Y.
I see, yeah. And that is wrong, really. So Qy is Yq. So yeah, thanks a lot.
Professor, so
yeah.
So this just means that so Yx can be say minus xq or something like that, and we say that q commutes with x and y. We want to make sure q is like a number, like in these things.
No, I mean they're in symbols. I mean they're indeterminates. There's some algebra. In the algebra, one of the rules is that there's this special object q, which you know, which commutes with everything, and the other objects, say x and y, whatever are the generators of that algebra, they q commute. So yx is equal to qxy. I mean, this is just a game we are playing. I mean, as far as we are concerned, we are just playing this game. What they mean, I mean, God knows what they mean. I mean, I don't know. So it's come from physics, I think, somewhere. And it's well, it's a beautiful thing, and you'll see what it's like. So what we want is let the q binomial coefficient I use the same symbol, but now I add a q here, and sometimes I forget the q, so then you remind me. Be defined y. So I will again do x plus y raised per n, and I will sum over this, and I have n choose k of sub q x raised by n minus k y raised by k. And the goal is to find what is the goal is what is this animal. Okay, so just what we did earlier, except which you did in high school, and now we've come to the crux of the matter for this. I mean, the new theorem of this course. And what is this guy? So I've just messed up a little. Go ahead. Sorry.
Oh no, Professor. I didn't realize my mic was unmuted.
Okay. All right. So let's do some calculations. Okay. So let's do some examples to get a handle on this beast. So of course, x plus y raised per 0 is going to be 1. X plus y raised per 1 is going to be x plus y. So nothing big that we get to know here. Okay. And x plus y square. So here we have x plus y, and we have xx plus xy. So this guy plus this guy plus yx plus yy. And this is x square, so x commutes with itself. This is xy. This is qxy plus y square. So this is x square plus 1 plus qxy plus y square. So now this is to choose 1, to choose 0 is 1, to choose 1, q is 1 plus q, and to choose 2 is 1. And do you want me to work this out? Let's work it out. We did it in the binomial case. And this is the reason I did it in the binomial case, that it will become easy. So what are the terms? We have x, x, x. We have x, x, y, x, y, x, y, x, x. Then we have two y's, right? So y, x, y, y, x. And then we have y, y. So this will give you x cubed. This will give you x square y. Now here one x has to shift, so this will give you qx square y. Here y shifts twice, so this will give you q square x square y. So these will give you terms 1 plus q square times x square y. Then these three terms will give you no problem here. This will give you a q because these two guys will change. And this will give you 2 times. So this y will come here, will add a q, another y will come here and add a q, you will get a q square x y square. So this will give you again 1 plus q square of x y square, and this will give you y cube. So do you understand this algebra? Is this okay?
Yes, Professor.
This algebra sounds okay?
Yeah, Professor.
We understand the rules?
Yes, Professor.
Okay. So let's carry on. So what is clear? So clearly, what we know is n choose k, this qk is a polynomial in Q. Then when q is equal to 1, then it reduces to n choose k, the earlier guy. Further, it's clear that n choose 0 is 1 for n equal to 0, 1, 2. N choose k is 0 when k is bigger than n. N choose n is 1. So those properties are okay. So this is when k is equal to 1. So these three properties are fine, right? Now, what is the appropriate? So here is the idea. The appropriate generalization to keep track of queues of binary strings is path from 0, 0 to n minus k, k in the plane. So let me do it by example. Let me take another color from doing this. So let's say this point is, well, let me make, this is 0, 0. Then I go up, then I go right. So let me go up again. 2 times right. And I go up and I go right. So suppose this is a path in the plane. Okay, so this 2 squares count as 1. So 1, 2, 3, 4, 5. So this point is 5 and then 1, 2, 3. Okay, and what I do is, so there are east steps I mark as X and north steps I mark as Y. Okay, now so steps are east, they're marked X, they have weight X, and north, they're marked Y. And how do I represent Yx equal to Qxy? So if I replace this guy by this chap, this is Yx, this is Xy, okay? Then I get a Q, extra Q, right? So I consider this box, this area, to be Q. So the point is, as follows. Here there is one, here are all these boxes underneath. So the area underneath the path keeps track of the power of Q associated with this path. So let me just do it formally. So you have X, Y, X, Y, X square, Y, X, right? So if you're shifting this Y, you get a Q. So you get a Q here. Then you shift this Y, you'll get 3 Qs. right? So then this will come here. Then you shift this y on the right, you will get 1, 2, 3, 4 Qs. So how many Qs do you get? So 1, 2, 3, 4, 5 y raised per 3. Do you see that? 1, 2, so there is, let me take a fourth color. 1, 2, 3, 4, 5, 6, 7, 8. Basically, each time you're shifting it, you're counting this box and you're replacing it by something like this, right? When you shift it, you replace it with this path. Then when you shift this, these three, you will replace it by a lower path and so on, and bring it down. That's what you do. Does that make sense? Are you getting that the Q is counted by the area underneath the path?
Yes,
Could you
Professor.
repeat? Could you repeat?
Sorry, I can't hear you. I don't know if it's my internet or your internet.
Professor, could you repeat the last part when you were showing it in the box?
Yeah, so what am I doing when I shift, essentially when I shift yx with qxy, pictorially I am going from this guy, this is yx, to this guy. So this area under this box is what I'm destroying essentially. So if I count all the areas, then I keep track of the power of q in this path. So
Professor, each
so for
jump,
example, this yx, the next step is qx x square y, and then rest stays over here. So y square x square y x. Now if I take one of these y's and shift it on the right, I'll get x square. If I shift this x square and take the other y, it's x square. So it will be 4 of those. So q raised to 5 x to the 4 y square times y. So that's y cubed x. Right. Now I shift these guys. So y will shift, each time y shifts, it give you a q. So there are 3 q's more which will come out. So q raised per 8 x to the 5 y cube. That's your final answer. So essentially this boxes keep track of, this boxes, the underneath the curve keep track of, underneath the path keep track of the q's, how many q's are there. So what am I saying more formally?
Professor,
I'm saying,
one thing. So each, so this makes sense when you say, okay, each path is, each jump in the path is a unit jump, right?
yes, yes.
Okay.
So yeah. So I mean the unit is q. I mean this area of a box is q sort of.
Okay.
The area represents q. I mean this area represents q because I want this guy.
Yeah.
Okay, so what am I saying? I'm really saying the following. I'm saying that if I take all the paths which are going from this point to this point, and I keep track of the area underneath the path, then I will get this number, n choose k. So what am I saying? I'm saying, we are saying the following. N choose k, well, is the sum q raised per, so it's a sum over paths from 0, 0 to, so weighted paths as above, to n minus k, k. N minus k means number of x's and k means y's, right? And this is the area under the path. P is a path and q raised per area under path. weighted as east goes to x and north goes to. And if you take all of these guys together, you will create this polynomial. So work it out. I mean, try with a term, let's say x plus y raised to 4, the term involving x square y square. Well, let's do, yeah. Work out this term. Find out all the paths which have two east steps and two north steps, and according to that, you work out the polynomial. See what you get.
Professor?
Yeah.
So always q to the power will be the power of sum of the power of x and sum of the power of y, right?
No. The area under the number of boxes.
Okay, yeah. So I was just thinking like from like in general, for example, if we see q to the power is 8, right? And x to the power is 3 and y to the power is x to the power is 5 and y to the power is 3. So I was just
Yeah,
so
but
I was just,
x to the power is, so we are just bothered about the coefficient, right?
yeah.
So this power is there, this is just the coefficient.
Okay.
And this polynomial is created like this.
Yeah. So it need not be the case that the power of q will be the sum of the power of x and the sum of power of y.
No. X's and Y's are separate, yeah.
Okay.
So
All right.
I just try this guy, you will get it. No issues.
Okay.
Anyway, let me write down the theorem. Let n choose k sub q be defined above. Then, so something like, I mean, we did the basic stuff, but something like Pascal's triangle. So the same thing as over here, the q here, and choose k, q. Oops. N plus k minus 1 or n minus k minus 1. N minus k plus 1. So let's do one first. So what are you saying? We are saying that n plus 1 choose k q is the generating function, paths as before, q raised for the area over here. So, and these paths are going from 0, 0 to n plus 1 minus k, comma k, right? So you have a path going from 0, 0 to some point here, which is n plus 1 minus k, right? So some path here. And this is of two types. So there are two buckets here. Bucket one is when the last guy is a north step, or let me do a east step first. When the last chap is an east, so some bucket here. So last is east, is x, and bucket 2 is when the last is over here. So you're starting from here, and the last guy is. So either the path ends with a north step or a east step. Okay. If it ends in a east step, Then if you chop this off, you will get a path which is going here plus these extra squares. How many squares are these? K squares. So bucket 1, there is the number of paths in bucket 1 is q raised per k and choose kq. And number of paths in bucket 2 is n choose. So this path is y calculates y is keeping track of k minus k, so it has one less y. So what are we saying? We are saying take all paths here and put into two buckets. Bucket 1, the last one is x. Bucket 2, the last one is y. Number of paths in bucket 1 is this. Number of paths in bucket 2 is this. Okay. So we have all of them together should equal this.
Professor,
Yes.
can you please once again explain the number of paths for bucket 1? How did we arrive at that?
So I'm looking, so I have a path, it goes from 0 to this point, right? N plus 1 minus k and k. Yeah?
Yes.
I look at the last item. Is the last item x or y? Is the last guy x or last guy is y?
Right.
If the last guy is x, then if I delete it, just like I deleted the last one over there, if I delete it, I get a path going to, n. So this point over here is n plus 1 minus k, I mean the x coordinate, and the height is k.
Yeah.
So this point will be n minus k and height will be k. So it will give me this guy. And by deleting the x bucket, I have deleted certain number of squares underneath it, right?
Right.
These are these k squares. So if I'm adding all the squares, which is what I need over here in the left hand side, then I need q raised per k times the number of squares here.
I am not following how we are multiplying q raised to k by this nkq.
If I delete this guy, so in a specific example, I delete, this is the last guy, right? I delete this chap.
Right.
Now I'm counting all these guys. So what else have I missed out in counting? I've missed out these chaps, right?
Right.
So these are the Ks which I add over here.
Right. No, I see how we are getting the k, but I don't follow how it's like how we are getting q to the power k.
Professor, one thing. So, doesn't this represent when we delete k boxes? Doesn't it correspond to the second term when we are raising q to the n minus k plus 1, and we are choosing nk minus 1 q? So, deleting x will correspond to the second term, not the first term, right?
Deleting x, no. We have x raised per n plus 1 minus k, y raised per k. And n plus 1 choose k. So on the left hand side, we have this term, n plus 1. So when I delete one of the x's, then I get x raised per n minus k, y raised per k. And that will correspond to n choose k in the second term. Okay, tell me this guy. When I delete a y, I used to have y raised per k earlier. Now if I deleted a y, I'll have a y raised per k minus 1 here, right?
Yeah.
Right.
But the x's stay the same.
Right.
Right.
So, okay, so have I made a mistake? Are you saying should be n plus 1? No.
It's fine, Professor.
Yeah, no, I follow how we get the second term of n choose k minus 1 of like base q, but I also see how we get q to the power k in the first one, but I don't see how we are like why we are multiplying q to the power k to n choose k base q.
Well, I mean, okay, so now let's go back to this chat. Yeah, so we are looking at this n choose case. So for a particular path, any particular path, I'm getting q raised power area under the p. And now
Right.
to this, I'm just adding. So think of adding an x to this path in the last step.
Right.
So when I add it to the x, then I am adding k more boxes. That's all.
Oh, okay, that makes sense. That makes sense.
So deleting is same as this guy. Okay. So yeah, I mean here the n stays the same, n plus 1 minus, but k is reduced. So it's basically n plus 1 minus k plus k minus 1, and that is why it gets k is reduced. So maybe it is n minus n plus 1 minus k. So yeah, so if k becomes, what am I saying? Nx returns stays at n plus 1 and minus k minus 1. This should cancel. Anyway, so I'm a bit confused now. So about how we get this term, work it out. Anyway, so let's see if the second part now. So the net result of all this is that you have confused me about the second part. But anyway, let it pass. So the second part, what we see is this, yeah, over here. How do we get that? So the way to get that is to observe that any path, right, which has um, um, uh, let's say each path which has uh, n minus k x's and k x's, k y's, this corresponds to another path with k x's and n minus k y's. So we just interchange by interchanging x with y, right? So there is a one-to-one correspondence, and one should get, when we add up all the q's in the same way, we should get the same result. So there should be some symmetry. So any part, let's say x's n minus k x's mean minus k east steps, and this is north steps, and we just interchange the two, it should correspond to another path with this guy, and then vice versa. So the number should stay the same, right? The number of such paths should stay the same, and the area sort of gets switched, from q power something to a q power something else. So what I'm saying is that you should get this guy. Um, so think about this a little bit. Here we are taking the sum over all the paths which have certain number of n minus k steps and k minus whatever I steps. So this is over all paths, which have two n minus k and which have certain area, and then this one will have all the paths up till n minus n minus, so it will go to k n minus k. So somewhere there is a symmetry which you can sort of work out, and this happens, and then using this symmetry, we get part. So basically, if you replace n plus 1 choose k by n plus 1 choose n plus 1 minus k, and then work out. Now the important part is, which now we run out of time, so I'll leave the rest as an exercise and maybe we'll look at it later. You got two terms. You got these two guys and they're both, you got two expressions for these. So if you compare the two, you can get an expression for combine the two, and you will get an expression for this. You just write it down. And if you iterate it, you will get a value which is one minus q raised per n minus k. So this is an exercise. And if you use limit q going to 1 minus q raised per k over 1 minus q equal to k, then we get n choose k is equal to n factorial over k factorial over n minus k. Yeah, you guys still there?
Yes,
Yeah,
Professor.
Professor.
Okay, so this I'm leaving as an exercise. Just try it out. What we are saying is
Professor, can you
that,
slide down to the second exercise?
yeah, I'll just do that. What we are saying is, if you compare these two terms, you'll get some expression with n choose k and n choose k minus 1. So that is this expression. And then if you iterate this, if you replace k by k minus 1, k minus 2, you get a product. And in the end, you will get k equal to 0 here. And then n choose 0, you know what it is. It's 1. So with the result that you can find an expression for this guy. And then there's some manipulation. You can, there's some manipulation that you can write as 1 minus q square up till 1 minus q raised per n. Divided by 1 minus q up till 1 minus q to the k, and 1 minus q up to n minus q raised per n minus k. And now if we divide both sides by 1 minus q raised to the power n and use this limit, then we can get an expression when q equal to 1, n choose k as n factorial over k factorial n minus 1. So this expression, we didn't have an explicit expression earlier. We had a recurrence relation, right? So what we got is, what we can do is, we can use this Q business to find an explicit formula and then take the limit and we get an explicit formula for this guy. Okay. So yeah, I mean, let me again think when I'm writing my notes about this last step, where I messed up somewhere, but I think it's right. And then you, yeah. So this is this non-commutative. This is the non-commutative binomial theorem. And it's a famous result. Many people have proved it. So this formula for n choose k, another place this comes out is it counts the, I mean, if q is a power of p, some power of p, then it counts the number of vector spaces, subspaces of dimension k of a vector space over a field of order e raised to alpha, something. So this comes up in many other contexts, the Q binomial coefficient, and we'll see it in few more contexts in this course. And somehow it's a polynomial which comes out very frequently, and it's obvious from here that it's a polynomial. It's obvious from the expansion that it has to be a polynomial. From this kind of calculation, it's obvious that it's a polynomial. Okay, so I'm done here. Next time, I don't know what we will do. I will decide.